power and energy design space. All right, so this is what we did just now. We have done, we haven't done that. Okay, for dynamic, you can reduce the VDD, you can reduce the transistor size. Okay, we haven't done multiple VDD and we haven't done clock gating. And for leakage, right, we will do this later. We have multiple thresholds, stack effect, pin ordering. So these are all the techniques that can be used to reduce power. Okay, next what we are going to do is multiple VDD. Okay, so as you can see here, dynamic power is a function of VDD, and decreasing the VDD decreases the dynamic energy consumption quadratically because it is a function of VDD squared. If you reduce, you will reduce the energy consumption quadratically. But it has a trade-off. It will increase the gate delay and decrease the performance. So if you reduce the VDD, it will have less voltage. So the circuit doesn't have enough energy to run as fast. Okay, so it will introduce gate delay. So so what you have to do, you have to determine the critical path at design time and use high VDD for transistors on those paths for speed. Use a lower VDD on the other gates, especially that drive the large capacitance, and this yields the energy benefit. Okay, what does this mean? Critical path. I will show you using the previous example. All right. So for this circuit on the left, let's say this is guy A, this is guy B, this is guy C, and this is guy D. Which guy is the slowest? Anybody?
A.
Slowest. Which has the highest delay? D, B, C,
D.
D. Okay, this guy, right? This guy, poor guy here, he is the slowest. Right? So he's the slowest because he arrives at the gate at t equals to 0.3 because he has father. This one, the guy, the finishing line is here. This guy, the finishing line is here. And this guy, the finishing line is here. So the poor guy, D, Mr. D, has to run very far and he arrives slowest. And he is known as the critical path. So in a chip, you have to always consider this critical path. They don't care about A because A is the fastest. They don't care. The speed of your chip will be determined by Mr. D because he is the slowest. So you have to help Mr. D. So if Mr. D is slowest, you have to give him more VDD so that he can run faster than A and B. If you do not put equal to Mr. D. If you cannot move the layout such that Mr. D has the same finishing line as everybody, you have to help Mr. D. You have to bagi dia bantuan sikit, bagi dia VDD. Okay. So this is what this means. Determine the critical path, which was Mr. D at design time, and use high VDD for the transistors on those paths for speed. Orang lain yang cepat tu, you don't need to give them a lot of VDD. You give them lower VDD so that you can save power. Okay, lower VDD on other gates, especially those that drive large capacitance, as this yields the largest energy benefit. Okay, so this will how your chip will look like, right? So for example, you want to reduce the dynamic power by reducing VDD squared. Okay, so if you look just now, which guy has to have lower VDD? So just now in the case yang tadi tu, A, B, C, and D, so everybody else will have lower VDD except for Mr. D. Mr. D is the memory, he will have higher VDD. So that memory can run faster. All the other guys, A, B, and C will have lower VDD 1.0. So this will save dynamic power of 30%. So you can see here, Mr. VDD is in the dark blue. Mr. D is in the dark blue and it will have higher VDD of 1.2. Okay. Hopefully everybody is not sleeping. Huh? Okay. Multiple VDD consideration. So the idea is you can use different supply voltage in the same chip, high VDD for critical paths, low VDD for non-critical paths. Okay, so you have to determine which is the critical path, and you put high VDD for that and lower VDD on the non-critical path. For low VDD, you prefer gates that drive large capacitance for best energy benefit. You can put 2 VDDs, but more is possible, but it makes your chip very complicated. So usually people put 2. So this is the path. So actually, if you are running a race, right, the gatekeeper of the race here is Mr. Flip-Flop here, Mr. Flip-Flop number 1, and the finishing line is controlled by another flip-flop. And if you have to run another race, there will be another flip-flop. So your combinational logic will be put in the middle. Combinational logic is the gates that are not involving the clock, such as NAND, NOR, XOR, or inverter. These are known as combination logic. Flip-flops are the sequential logic or the gates that have timing, right? So the data will propagate through different data paths between registers or between flip-flops. The path will mostly differ in propagation delay time. So you see this guy, he has to go through 1, 2, 3 gates. This one has to go to 1, 2, 3, but this guy is an XOR. XOR usually comprise of more than one gate. And this guy has only 2 gates and very simple. So he's going to arrive the fastest, right? So maybe this guy is going to be the critical path. So you know that you have to give him more VDD. This you can control in your layout. You are going to hook up. You remember you draw the VDD in the layout, so you are going to hook him up to a different VDD. Okay, so the frequency of the clock signal depends on the path with the longest delay. So let's say this guy, this path 1 takes 10 nanoseconds. This path takes 20 nanoseconds. This path takes 5 nanoseconds, right? So we have these other gates over here. This path takes 15. This path takes, what did I say here? 5. This one takes 5. Okay, which one is the critical path? Which path? Which is the longest delay? What is the longest delay? Anyone? What is the time with the longest delay? How many nanoseconds?
10.
Longest, not.
$20.
20. So you can see out of these many, this is the highest delay, 20 nanoseconds here. Okay, so this is known as the critical path. The frequency F equals to 1 over 20, which 20 nano is what? Is 0.5? No, 0.05 gigahertz, correct? One over 20, 1 over 20 is 0.05, correct? Gigahertz. Okay, so the others will have higher speed. This is 0.1 gigahertz, right? This is 0.2 gigahertz. 1 over 5? Yeah, 0.2 gigahertz and so forth. So the frequency of the clock will follow the longest delay path. So even though this is 5 nanoseconds, it doesn't mean that your circuit is running F equals to 1 over 5. It is not true. It will follow the longest delay. So it will follow this. So you have to help this critical path so that your overall chip speed will become faster. Okay, so how do you help them? You are going to do different voltage supply. So this is known, minimum energy consumption is achieved if all logic paths are critical, or all logic paths have the same delay. But if certain parts have higher delay, you can do clustered voltage scaling, meaning you are going to put different VDDs. So for example, in this case, this one is the critical path. It has the highest path and it has the most gates that it's passing through. So it will be connected to VDD high. And this one is the lower path. It will be connected to VDD low. Okay. Each path starts with VDD high and switches to VDD low, the gray, when delay slack is available. So when this guy is he knows that it doesn't have to pass through so many gates, it will switch to the lower voltage, lower VDD. The level conversion is done in the flip-flops at the end of the path. Okay, so you can see here